we can easily apply this concept into one applications we normally use for solving beam problems. In other words, if we have a beam like this with a simply pin end supporting one with a pin supporting one at one end and another roller, for example, at the other end, and now we have a distributed load. We have a distributed load like this. The question is, can we find an equivalent concentrated load acting on somewhere, which is the summation of the distributed load? However, the corresponding resultant moment is equal to 0. So that originally you have, let's say this, you have a distributed load acting at every location of the beam, going down, for example. So this one is equivalent to just one concentrated load acting on somewhere. And we always do this kind of equivalent because we move all the forces into this point, we got the resultant force. This resultant force is always the summation of all forces. That's chapter 3. And then we can, in general, calculate the resultant moment. But if you carefully pick a certain special point, then the resultant moment happens to be 0. It's very important to locate this one. After we can locate this point, then we can calculate reactions. Otherwise, it's just based on the distributed load. How are we going to calculate the reaction, the support? We have no concept calculating the reactions if we see the distributed load. So that's why we want to grab the same concept we got from the centroid, and then we can find that point. This point, in fact, is a centroid based on this geometry. Because the centroid concept said when you move all the force to that point, then the corresponding resultant moment equals 0. So that's why this and the previous centroid concept is consistent. It's the same thing. Okay, how are we going to do it? In reality, if the profile or distributed load is quite complicated, you finally still end up with the integration. Okay, so if you look at each tiny force distributed through the whole span, so then each one multiplied with a tiny area, that's the total force, and then you add them all together, and that's the summation. That's summation of all forces. That's equal to the resultant force. Okay, so that's resultant force. In fact, if you look at this more carefully, everywhere you have a W, you have W which is distributed along the whole span, and times dA, and you add them together. What's this one? In fact, this is the area. So finally, you end up with this area. So this area is representing the equivalent resultant force. But keep in mind, this area, when we look at this area, in reality, the unit of this area is not in terms of meter square or in terms of foot square. It's not. In reality, you look at this vertical direction, that is the load intensity. That's going to be Newton per meter. And then this is meter. So Newton per meter times meter, that's finally end up with Newton. That's why, in reality, it's the force. It's the resultant force. Similarly, you want to locate this point. You call this point is x bar. From here to here, it's called x bar, right? So in order to locate the x bar, then you calculate the moment due to all the forces at this point, which is equal to the moment due to this equivalent force acting on this point, and they are equal with each other. That's why you can find out x bar times a, and then equal to the integration of x dA. So that's why x bar equal to integration x dA over a. That's, again, the same concept as we called in the previous centroid. Okay? So once we understand this location is simply the centroid, then we can take advantage of the composite rule to help us out to locate, to identify the location of the centroid. So let me just give you an example just to show you how we're going to find out that centroid location. Again, if we do not want to use the real integration, then we have to somehow simplify the distribution of the distributed load a little bit simpler. So let's say this time we have a linearly distributed load acting on the beam. So a beam supports a distributed load as shown above here, but it's linear distributed. Now we need to determine the equivalent concentrated load. Number one, is there equivalent concentrated load acting on somewhere? We need to locate that somewhere, and so that you have the resultant moment. Okay, and that's called the centroid, right? And then after we get this one, then we can also calculate reactions at the support. That means what is the reaction due to this roller? What is the reaction due to this pin end? Same thing, first of all, let's calculate the centroid of this one. So then we're going to split this area, which is this, identically this, right? So you have this one with a 1.5 kilonewton per meter, that's given here, 1500 Newton per meter, this one, and this one is 4500 Newton per meter. Okay, so we put from here to here 1.5, from here to here 4.5, or you say 4500, either way, you use the kilonewton or Newton, right? And from here to here, that's the whole span of the beam, which is given at 6 meters. So that's why we put 6 meters here. Now, it's our job to locate the centroid of this geometry. So, from the previous chart, we don't see this picture, right? So from the previous chart we have here, there's no such geometry. So then we need to split this a little bit more complex geometry into a few simple ones. So obviously, there are many ways you can separate, by the way. You can easily separate based on these two triangles, okay? So totally is this one, it's a trapezoidal shape, in fact, right? So when you connect this one, then this total trapezoidal shape should include one triangle and another triangle. Okay? Putting together, that's the overall shape, geometry, the area. Now, how are we going to locate the centroid? We do the same thing. We create a chart first. Components, we only have two triangles. We call triangle 1 this. We call triangle 2 this one. And now we need to calculate the area for each triangle. So what is the area of this triangle 1? Well, that's a 6 meter, right? From here to here, 6 meter times this. But again, keep in mind, the unit of this one is different. This is 1.5 kilonewton per meter. So 6 times 1.5, and don't forget divided by 2. 6 times 1.5 divided by 2, that's going to be finally 4.5. Okay? And if you want to deal with unit, that's supposed to be kilonewton. That's why you put the kilonewton here. So this is now the real area. It's a virtual one based on the plot you have. Similarly, what's the area of this triangular shape 2? That's the base with a 4.5 multiply 6 and divided by 2, right? So 4.5 times 6 divided by 2, that's 3 times 4.5, so you end up with a 13.5. And just again, the unit is kilonewton. Okay, so that's the first column, the second column, and you can add them together, you get the total area, which should be used later on. This plus this, you get 18, right? Now, we need to identify X bar, Y bars in each small one. The reason we don't have Y bar, I'll explain to you. I'll talk about X bar first. So what is X bar for each triangle? Triangle 1. This is the triangle 1, right? So this is the triangle 1. What is X bar? That is from the centroid of this local to the original point. This one. This is the original point. This one. So again, from the centroid to the base is what? From the centroid to the base is 1/3 of this total. From 1/3 from this vertex to the same base. So this total is 6. 1/3 means 2. That's why I put 2 here, or you can write down 2 here. So 1/3, right? Now, second, what is the X bar based on the second triangle, this one? So let's say this is the centroid. So now X bar should be from here to this time to the vertex this time. Because this is X and this is the Y, right? So go to here. So this, because from here to the base is 1/3, then from here to the vertex should be 2/3, because total has to be 3/3, right? So 2/3 of this total, which is 6. 2/3 of 6 is 4. So that's why you put 4 here, or you write down 4 here. Okay, so we got X bar for the first one, X bar for the second one. In general, you're supposed to list Y bar for any this kind of beam problem, because we do not need to locate Y bar, because we only need to know finally the force is acting on beam or somewhere, which can be characterized by X bar only. So you don't have to say, is this force acting on here or here? It doesn't matter, because in the same line, the force can move along the force direction. So that's why for this specific problem, you do not need to calculate Y bar. Okay? So once we get X bar, and then we have the summation, well, we have X bar times each cross-section area, times simple geometry area. You get this, you get this, you add them together. So finally, this one divided by this, that should be the overall X bar. So 63 divided by 18 with here, that is the capital X bar. which is the overall centroid based on this total complex geometry. So in other words, finally, you can put a force, which is the equivalent concentrated load acting on this point from here to here is 3.5 as you calculated from this composite rule. The second question is, what is the total force? That is basically the area, or the summation of all the forces, which is the area. So that's why this 18, in fact, is the total concentrated force, with simply the area. You may say, how come force can be an area? Well, sometimes it is, because we have the same unit. Any questions? Okay, so that's the first part. We are successfully transferring this distributed load into a simple concentrated load acting on this location. So once we get this, then we can answer the second question. The second question is, calculate the reactions at the two support. Okay, so first part we're done. What is the equivalent concentrated load and acting on where? And the answer is, it's acting on this location from here to here is 3.5, or in other words, from here to here 2.5. And the concentrated load is 18 kilonewton. So that's the first question, the first answer. That's the answer for the first question, right? Second question is the reactions. That's fine. You need to plot the free body diagram based on chapter 4. So this is the rigid body, and then you cut this one, you gave the reaction force. You cut this one, you gave two reaction force because there's a pin. So then what we end up with, rigid body here, you gave one reaction, you call it A. You gave another reaction, you call let's call this BX, and this called BY, okay? Because BX in fact finally equals 0, but you're supposed to write BX and BY here. And then, of course, you have a force acting here. This is what we call the free body diagram, right? So based on this free body diagram, we need to list 3 equations from chapter 4. Number 1, the equation for summation all the x component equals 0. And you look at this, how many forces along x direction? There's only one, bx. So that's why you get bx equals 0, right? So it's only force. You plug in this equation, that's bx equals 0. So it's bx equals 0. Now, you are considering the second equation collecting all the force in y direction. Then you're going to have what, a plus by equal to 18. Okay? So a plus by equal to 18. And you leave that equation there for a while, because from that equation you cannot solve for 2 unknowns. And then the third equation should be the moment equation. So you need to take a moment at the arbitrary point. Which point you want to choose? You can choose point A or you can choose point B. It's up to you. Let's say we choose point A. So what are the moment due to all the forces at point A? So this force itself has no contribution, but you have this force, 18. 18 times the short distance, F times D, right? 18 times the short, this is short distance as well. So 18 times 3.5. 18 times 3.5, that is the moment of this force about point A. This one, you hold point A. This has the potential to rotate this rigid body clockwise. You put a negative sign in the front. Okay? Now, how about this force? You call By. So By times the short distance, that's here, that's 6. So By times 6 is the moment due to this force at point A, and this is counterclockwise. So you put a positive sign. And this one minus this equals 0, because Bx doesn't contribute either. Bx is passing through this point A as well. So from this equation, immediately you get By, right? Because that's the only unknown involved in this equation. You get By. By is 10.5. So now you got the By equal to 10.5. By plus A equal to 18. Obviously you get Ay. You don't even need to use this equation. You just collect all the forces in y direction. You get Ay equal to 7.5. Because Ay plus By, 10.5 plus 7.5 must be balanced with 18. So that's why you got the reactions. Okay? On the other hand, if you say, okay, I don't want to use this equation, I want to use the moment equation at point B. Is that okay? Of course it's okay. You can use this equation, immediately you get Ay as well. Any other questions? Okay, so basically this chapter we talk about 2 things. Number 1, we talk about how to calculate the centroid of an area, which is always the same location as what we call the center of gravities. And by definition, that's an integration of x times dA and over A. or y dA integration and then divided by a. And you have to deal with integration. And many times, as an engineer, we may not want to do the integration, then you basically use a composite rule. If you want to use composite rule, then somehow you need to memorize at least some of those popular ones, allowing you later on to separate in terms of each simple geometry, and then you can still get work done, because that is the summation of a limited number of simple geometries. So that's the first part, calculating the centroid based on a relatively complex geometry. The second part, which is quite related with the first part, but this time we need to calculate the equivalent concentrated load based on the distributed load acting on the beam. And that's the same thing. You even do not need to calculate both x bar and y bar. You only need to calculate x bar only. Okay? So typically, for example, like this case, you just need to split this one into two or more simple geometries. And by the way, this is not the only one you can split. Very easily, you can split this overall geometry into one rectangular shape plus another triangle, in fact, right? So you finally end up with the same thing.